Before investigating a factory's operations, we first selected the most suitable company. Our team evaluated 3 manufacturing candidates using a 10-criteria matrix. We looked at accessibility, management cooperation, and learning value. Among all candidates, Anveng Packaging received the highest score of 622 points. This made it the perfect choice for our operations management investigation. Let's take a closer look at Anveng Packaging. Officially registered as Anveng Single Member Limited Liability Company, the company specializes in packaging design, printing, and plastic films. Operating since the early 2010s, the company has over 15 years of experience in northern Vietnam's packaging industry. Anveng produces PA and PP plastic packaging films for food, consumer goods, and industrial applications. The company serves over 360 customers across northern and central Vietnam and exports to Japan, France, and South Korea. In Vietnam's 8 to 10% annual growth packaging market, Anveng competes through fast delivery, flexible customization, and low minimum order quantities, despite pressure from low-cost imports and rising resin costs. Anveng has a centralized management structure with 4 departments: printing, laminating and slitting, bag making and quality control, and sales and warehouse. The company employs over 40 staff, with an average age of 28, reflecting a young workforce. The supply chain starts with PE and PP resin procurement, followed by in-house production, quality control, and direct distribution to customers via company or third-party logistics. Most orders come from long-term business relationships. Now, let's analyze the current production system. Anveng's production process consists of 13 sequential steps. It starts with raw resin receipt and ends with product delivery. Although the process follows a logical sequence, only 2 formal quality inspection checkpoints are in place, one after raw material receipt and another before shipment. This means defects created during production may remain undetected until the final stage, increasing material waste and rework. The 13 production steps are grouped into 5 stages: resin processing, film blowing, printing, cutting, and finishing. While the process is generally balanced, waiting times increase during printing, cutting, and especially finishing due to machine changeovers and QCQs. Quality inspection is mainly conducted at the beginning and end of production, allowing some defects to go undetected until final inspection. The main bottleneck is the finishing stage, where quality inspection, labeling, and packaging are handled by only 2 workers. Additional issues include cutting delays, QCQs, and late defect detection, leading to rework and material waste. The analysis also identifies 6 lean wastes, including unnecessary transportation, motion, inventory, defects, overprocessing, and underutilized labor. Overall, Anveng's production system is moderately effective, but constrained by a finishing stage bottleneck and late defect detection. The report recommends expanding finishing capacity, adding earlier inspection, optimizing corona treatment, implementing condition-based maintenance, and standardizing key processes. The KPI dashboard summarizes performance across throughput, quality, downtime, cost, and safety. The baseline KPIs show all indicators are below target, highlighting key operational issues and providing benchmarks for proposed improvements. Anveng's production flow clearly mapped. The focus now shifts to a critical question: why does quality keep failing? Anveng's QC records reveal a persistent 8% to 10% defect rate per batch, primarily driven by film tearing and gauge non-uniformity. In B2B operations, these thin patches snap under tension on customers' automated wrapping lines, causing immediate shutdowns, complaints, and costly rush replacements. To find the root cause of these quality issues, the team applied an Ishikawa fishbone diagram using the 5 meters framework. Operators adjust the blow-up ratio burr entirely based on personal experience without documented parameters. Machine, polymer buildup on die lips and air ring wear cause uneven airflow and asymmetric cooling. Material, melt flow characteristics vary between resin batches, compounded by inconsistent internally recycled blends. Method, current SOPs focus strictly on end-of-line inspection rather than real-time process stabilization. Measurement, Thickness checks rely on periodic handheld gauges instead of continuous monitoring, catching defects too late. In conclusion, while man, machine, and material act as immediate triggers, method and measurement are the critical failures that allow defects to propagate downstream. Therefore, our priority is strengthening real-time monitoring and standardizing operator decisions through documented parameter windows. To bridge the gap between these quality failures and operational practices, the analysis shifts focus to the manufacturing floor by evaluating the current standard operating procedures, which primarily concentrate on the critical stages of extrusion and film blowing. NVIN's current SOP lacks early detection mechanisms, scoring poorly due to unwritten parameters, zero inline thickness checks, and rigid calendar-based maintenance. These operational gaps directly introduce workplace vulnerabilities, which are systematically evaluated in Table 4.2, Safety Risk Assessment for Extrusion and Film Blowing Operations. Beyond quality gaps, our assessment identified 3 high-risk steps for operators: extrusion burn risks during manual die lip cleaning, film blowing entanglement hazards from moving rollers, and slitting laceration risks during blade changes or jam clearing. Occupational safety directly drives manufacturing performance. Incidents cause costly line stops, while operator fatigue from heat, noise, and pressure leads to bubble instability and thickness defects. By improving safety, we secure process stability and product quality. Specifically, condition-based blade maintenance and optimized corona treatment have slashed operator exposure to high-voltage hazards and ozone gas by 40%. Based on the findings from the previous analysis, we developed a proposed standard operating procedure, or SOP, to improve NVIN's production process. The proposed SOP expands the original 13-stage process into a 14-stage workflow by introducing 1 new step and 5 modifications. These process changes bring improvements in 5 key areas. Product quality is improved through earlier defect detection and real-time monitoring. Workplace safety is enhanced by introducing condition-based blade maintenance. Waste is reduced by eliminating unnecessary processing. Productivity is increased through shorter queue times, fewer production interruptions, and higher throughput. To measure these improvements, a KPI dashboard is developed to compare current performance with the expected performance after implementing the new SOP across quality, productivity, safety, and cost indicators. The financial analysis begins by identifying the costs caused by the current production problems. The total implementation cost of 0.9 billion Vietnamese dongs spans 6 initiatives. The second finishing and packaging station, VN 0.3 BN, is the largest item, covering workstation setup, labeling equipment, QC testing unit replication, and installation labor. Based on these estimates, the project achieves an expected return on investment of approximately 189%, with a payback period of around 4.2 months. The proposed SOP improves operational performance while delivering strong financial returns, making it a practical and worthwhile investment for NVIN. Overall, NVIN Packaging has a well-structured production system but is limited by process variability, delayed quality inspection, and finishing capacity. The proposed improvements are expected to increase productivity, improve quality and safety, reduce lean waste, and generate annual cost savings of approximately 2.6 billion Vietnamese dongs, providing a strong foundation for sustainable growth.